Right now, 99% of the world's international data is traveling through cables stretched across the ocean floor. Not satellites, not radio towers, glass, strands thinner than a human hair, carrying nearly every message, transaction, and search you send across a border. But glass doesn't survive the deep sea on its own. So how do you armor something that fragile for 25 years beneath the ocean? Popular belief credits satellites with carrying the modern internet, but the actual infrastructure is grounded on the ocean floor. Over 99% of all intercontinental data traffic moves through submarine cables. Satellites handle only a minor fraction of global bandwidth, operating primarily as broadcast links and remote backups for isolated regions. This massive underwater network is the direct descendant of Victorian industrial engineering. In July 1866, the steamship Great Eastern successfully laid the first permanent transatlantic telegraph cable, connecting Ireland to Heart's Content, Newfoundland. This breakthrough shrunk communication times across the ocean from weeks to minutes, proving that reliable undersea links were possible. Today, over 1.5 million kilometers of cable trace the seabed. The global internet relies on this vast network, but the engineering challenge is unprecedented. Modern designs must scale up a 19th century survival strategy to shield microscopic strands of glass, keeping them completely safe from the crushing pressure and physical hazards of the ocean floor. This is the physical reality of the cloud, a massive, silent, heavy industrial network hidden beneath the waves. At the center of this heavy industrial network lies a striking engineering paradox. While the finished cable is massive, its internal function relies entirely on pure glass. This microscopic core is where international data transmission begins, operating far out of sight on the ocean floor. Each individual path is composed of single-mode optical fiber, selected for its extreme efficiency over thousands of miles of long-distance transit. At its absolute center is the light-carrying core, measuring just 9 micrometers in diameter. To put this scale in perspective, a typical human hair is roughly 75 micrometers wide. This means the actual pathway for global data is approximately 1/10 the thickness of a single human strand. Surrounding this delicate core is a second layer of glass known as the cladding, which brings the total fiber diameter to 125 micrometers. The cladding has a different refractive index, acting as a continuous internal mirror that traps the light, forcing it to bounce cleanly along the core without escaping. Left bare, these ultra-pure glass strands are incredibly fragile. They would instantly fracture under the physical stresses of deployment or the crushing weight of the sea. To protect this vulnerable core, the fibers are bundled together and immediately encased in their first true metallic shield, a hermetically sealed stainless steel tube. The steel is drawn and welded in a continuous industrial process directly around the glass. This creates a rigid, pressure-resistant barrier that isolates the fibers, ensuring they remain completely dry and safe from the immense forces of the abyss. This steel-encased core serves as the fundamental foundation for all heavy armor to follow. If the stainless steel tube is ever breached, seawater must be prevented from migrating along the cable interior. To solve this, the internal voids are flooded with a thixotropic water-blocking compound. This dense petroleum jelly or bitumen-based gel blocks or slows water ingress, locking the moisture in place so it cannot flow freely down the line. But transmitting data across vast oceans requires continuous electrical energy. Because optical signals naturally degrade over immense distances, they must be boosted. Spaced every 50 to 100 kilometers along the ocean floor are repeaters, undersea amplifiers that rebuild the fading pulses of light. To keep these amplifiers running, the cable functions as a high-voltage power line. Surrounding the protective steel core is a heavy conductor sheath, formed from copper or aluminum. This layer carries a high-voltage direct current of up to 10,000 volts, fed directly from specialized power stations on shore. This configuration creates a dual-purpose system, a single line that simultaneously guides light through its microscopic center while carrying thousands of volts of electricity through its outer metal sheath. The engineering must withstand both the crushing physical environment of the abyss and the absolute isolation of the deep ocean. The system has to survive not just the sea itself, but the immense distance between landfalls. The mechanical design of the cable changes based on its destination. In the abyssal plane, miles beneath the surface, the cable requires surprisingly little external armor. Here, the dominant design constraint is weight. To prevent the cable from breaking under its own immense weight as it is lowered from the ship, the outer diameter is kept between 17 and 25 millimeters, roughly the thickness of a standard garden hose. But as the cable approaches the continental shelf, the threat profile shifts dramatically. Hydrostatic pressure yields to human activity. In water depths shallower than 500 meters, fishing trawlers, dragging anchors, and marine life pose constant hazards, accounting for over 80% of all cable faults. To survive these shallow zones, the cable undergoes a massive physical transformation. Manufacturers apply double or even triple layers of heavy steel armor, increasing the cable's diameter and weight significantly. This transition from delicate core to heavy industrial armor happens on a massive scale inside the factory. At the center of this process is the Planetary armoring machine. This colossal rotating carousel holds dozens of large wire reels, spinning them in a slow, hypnotic orbit around the central cable core. In a single, continuous pass, the machine wraps 24 to 48 high-tensile galvanized steel wires around the core at a precise helical angle. The low-frequency hum of the massive drive motor and the rhythmic whir of the spinning carousel mark the moment where raw steel binds with glass. This heavy outer armor ensures that the fragile light waves traveling through the center remain uninterrupted, even when subjected to the violent grinding of the shallow sea. Validation begins in high-pressure chambers that simulate the abyssal depths. Here, hydrostatic testing subjects the sealed structure to crushing forces exceeding 80 megapascals, the equivalent pressure found 8,000 meters below the surface. This proves the structural integrity of the outer layers remains absolute under the weight of the ocean. To guarantee the cable can withstand the physical strain of installation, hydraulic tension rigs pull the armored line to its limits, verifying its tensile strength under extreme launch loads. Simultaneously, technicians perform high-voltage direct current checks, running thousands of volts through the conductor to confirm total electrical isolation from the surrounding environment. These industrial trials certify the cable not as an experimental assembly, but as a robust machine. With its systems verified, the cable is rated for a nominal 25-year service life, ready to endure decades of continuous operation in the deep. The completed armored line is wound directly onto massive rotating drums, holding up to 5,000 tons of cable. From these manufacturing bays, the line is spooled into the circular storage tanks of specialized cable-laying vessels. As the ship transits, automated winch systems feed the line into the sea under a controlled tension of 10 to 30 kilonewtons. In shallow waters, a heavy sea plow digs a trench, burying the cable 2 meters down to isolate it from anchors and commercial fishing nets. If a fault occurs, technicians use optical time domain reflectometers to pinpoint the break, drag the seabed with grapnels to retrieve the line, and splice in a fresh armored segment. Once lowered back down, the line disappears into the silt, operating in silence on the ocean floor. At the ocean floor, this heavy industrial armor quietly secures our hyper-connected future for decades to come. The digital world remains bound to the physical deep, Thanks for watching. If you enjoyed this look at hidden engineering, subscribe for more.